Okay, so this is our next topic, which is the design of pressure vessels. Okay, so what are these pressure vessels? Okay, so pressure vessels, these are simply containers having pressurized fluid. When I say fluid, it would mean a liquid or a gas. Okay, so the most common sample of this pressure vessel is our water tanks. Okay, water tanks at home. So we have these water tanks. Commonly, they are in cylindrical form, and if you observe, there is also a dial, okay, or a gauge, okay, which signifies the pressure inside the vessel. Okay, so that would mean the pressure of the fluid inside the vessel. Okay, so these pressure vessels. Okay, so the pressure vessels which we commonly use, they are of different forms. Okay, so commonly they are cylindrical or in a form of cylinder. Second one, there are those that are in a form of sphere, and then there are other types. Okay, so the other types that include cubic, okay, cubical. We have also rectangular. Okay, but then this others form of pressure vessel, these are fabricated. Okay, they are not commercially available. Okay, so what is commercially available would be the cylinder type at saka yung spherical. Okay, so our focus on the design of this pressure vessel will fall onto these two. Okay, so it's limited to cylinder and sphere since these are the most commonly used ones. Okay, so the cylinder, okay, this is more space saving than that of a sphere. Okay, so if you are to increase the volume capacity of the vessel, okay, it is much advisable to use the cylinder. Okay, so we recall the volume of a cylinder. The volume of the cylinder would be area of the base, that would be pi r squared, and then you multiply that by the height of the cylinder. Whereas for the sphere, volume of the sphere, that's equal to 4 over 3 pi r cubed. Okay? So these are the two equations which involves the volume of the cylinder and the sphere. Okay? So as I have said earlier, okay, if you are to increase the volume capacity, okay, it is advisable to use the cylinder. Why? Okay? This is more space saving than that of the sphere. Okay? Say, let us have first the sphere. You want to increase the volume of the sphere. So what will you do? You simply increase the radius or you increase the diameter of the sphere. But then, increasing the diameter of the yung sphere natin, that will entail a large, okay, area, okay, for this pressure vessel to be mounted. Okay, so it will entail a bigger area, not unlike that of a cylinder. You want to increase the volume of the cylinder. So you can increase the volume in two ways. Okay, one is to increase the diameter or the radius. But then increasing this again will be the same as that of the sphere, that you need a large area. Okay? But then, you can also increase the volume of the cylinder by remaining, okay, or by maintaining the value of the diameter, but increasing the height. Okay? So, you have to increase this height. Okay? So, the space that it will consume, okay, the land that will it consume, okay, for the mounting of this pressure vessel will be the same because you have the same diameter, okay? Only that, yung height natin, siya po yung atin na i-increase, okay? So, increasing this height will increase the volume. Okay, but then the area occupied, the land area occupied by this vessel will simply be the same. Okay, that is why most of the industries, okay, they are using the cylindrical pressure vessels, okay, other than, okay, this sphere. Okay, so preferably to use the cylinder than that of the sphere. There are those industries that make use of this spherical vessel, but then they are limited only to those fuel or say fluid that are of small quantities only. Okay? It is because nga po of the space that they will occupy. Okay? So again, on our design, we will be limiting our design on the most commonly used type of the pressure vessel. Okay? That includes the cylinder and the sphere. Okay? So how do you create these pressure vessels? Okay? So it comes simply from a sheet of metal, okay? And then from the sheet of metal, you come up with this cylinder, okay? So it is simply a sheet of metal of a defined length, width, and then you have there the thickness, okay? The thickness being used, okay? So this refers to the thickness. Yan. So a sheet metal, a plain sheet of metal, you have to roll it, okay? And then once you roll, okay, the two ends will be joined using a weld or a rivet, okay? So this must be joined, okay, in order for you to have this cylinder, okay? And then you put in the same material, okay, for the cap, okay? So i-weld din po yan all throughout the edges, okay, to come up with your pressure vessel. Okay, so that is how you obtain, okay, or how to create the pressure vessel. Now, when we say we design the pressure vessel, what we are up to is the dimension. Okay, so what particular dimension is being determined in these pressure vessels, okay? So particularly, we are after the thickness, okay? So this is the thickness of the plate, okay? That is being used to create your cylinder or your spherical vessel, okay? So we are after this. You look for the most appropriate thickness, okay, of the plate. Okay, so that is what we are designing in a pressure vessel. Now, with regards to this thickness, we have what we call thin-walled vessel, and then the other one is a thick-walled vessel. Okay, so how do you know if a vessel is thin-walled or thick-walled? Okay, so it is not only the thickness that is being evaluated for it to be called thin-walled or thick-walled. Okay, in particular, okay, we are after this what we call limiting criteria. Okay, so you look at the limiting criteria. So the limiting criteria is the ratio between the thickness, okay? It's the ratio between the thickness and this one is the inside diameter, okay? So thickness over the inside diameter, it should be less than or equal to 0.1, okay? If it is within this range, then we say that the pressure vessel is thin-walled, okay? But then if the value exceeds 0.1, That's the other way around. You call it thick-walled pressure vessel. Okay? So what is basically difference between a thin wall and a thick wall? Why is it necessary that we know if it is thin wall or thick wall? Okay? So they have something, it is something to do with the value of the stresses. Okay? Say for example, okay, say for example, we take the cross section of a vessel. Okay, so this is the cross section of the vessel. So this is the outside surface. Okay, and then this is the inside surface, for example. And then this pertains to the thickness. Okay, so this is the thickness T. And here is the inside wherein the pressurized fluid, say gas or liquid, is inside. Okay, so this the pressure is inside the vessel. Okay, again, this is the thickness, and then this is the outside surface of the vessel, wherein it is most exposed to the air na nasa labas po. Okay, so most probably air po yung nasa labas nito or any other gas. Okay, as stated in the problem. But then, if not stated, we assume that atmosphere or the outside air would be the one in outside yung atin po vessel. Okay, so here is the thickness that is a requirement in the design of a pressure vessel. Now, so in terms of the stresses, what is the difference between the thin-walled and the thick-walled vessel? Okay. Okay, so let us have here some state points. Okay, so let us have here point 1. Okay, so point 1 is a point at the surface, okay, outside surface of the vessel. Okay, we have here point 2. Okay, point 2 is at the thickness. Okay, and then you have here point 3, that is at the inside surface. Okay, so 3.3 is inside surface, 2 is along the thickness, and 1 is at the outside surface. Okay, so which among this point is in direct contact with the pressurized fluid? 1, 2, or 3? Hello?
3 po, ma'am.
Okay, so 3 is in direct contact with the pressurized fluid inside that of the pressure vessel. Okay, now, in case of the stresses, say, we are to determine the stress at 1, the stress at 2, and the stress at 3. Okay, the values of each stresses in each of this point, okay, they are assumed to be equal if it is thin-walled. Okay, if it's thin-walled, the value of the stresses is almost uniform. Okay, that is in a case of a thin-walled. But then, in a case of a thick-walled vessel, okay, the stress at 1, the stress at 2, the stress at 3, okay, they have different values. Okay, you cannot assume them to be uniform. Okay, there is a large discrepancy on their values. Okay, the one which is in direct contact with the pressurized fluid, that has the highest value of the stress. Okay, so if you are to compare these 3, okay, you have their stress at 3. Okay, this is the highest. Okay, that is in the case of a thick-walled vessel. Okay, so with this reason, okay, we are to determine, okay, on our design first whether, okay, it is a thin-walled or a thick-walled vessel. Okay, so that would be your first step in the design. Okay, our first step of the design is to determine whether it is thin-walled or thick-walled. So how will you do it? You solve for your limiting criteria. Okay, thickness over the diameter, it should be less than or equal to 0.1 to be called a thin wall. Okay, otherwise thick wall po yan. Okay, Now, if you identify that it's a thin-walled vessel, then you have a defined procedure, okay, that you will be using, okay, to design this member. Same thing with a thick-walled vessel. Okay, so this is most likely similar to that of compression. Okay, members under pure compression, wherein you have their different cases, case 1, case 2, case 3. Okay, which depends on the slenderness ratio. Okay, so dependent upon the slenderness ratio are the cases. In each of the case, you have the procedure that you will be using, okay, to design these members. So basically, the same as this pressure vessel. Okay, so here, the first step that you should do is to determine the limiting criteria, okay, T over B sub I. Once you know it's thin-walled, so you follow procedure for thin-walled. And once you know it's thick-walled, there is also the procedure in designing a thick-walled vessel. Okay? Nakuha po ba? Naintindihan po ba? Hello?
Yes po,
Yes
ma'am.
po, ma'am.
Okay, good. So, let us now take the case of a thin-walled vessel, okay? Let us have first this one, the thin-walled vessel. But then, for a thin-walled, we will consider both, okay? One cylindrical in form and then the other spherical in form, okay? So, let us have the first one here. Okay, so the first one is a thin-walled and then cylindrical in form. So we call it thin-walled cylinder. Okay, so how do you design a thin-walled cylinder? Say this is our cylinder. What we do first is to cut it, okay, using cutting plane AA prime. So we cut it this way. Okay, so this is the cutting plane AA prime. Okay, say you cut it here. Okay, then we come up with the section. Okay, so this is now your cut section. Okay, so here is the forces that is applied. Okay, and this is the simply the thickness of the plate, okay, that we have. Okay, this is the thickness of the cylinder. Okay, so with that, we come up with our induced stress. So this is our induced stress. So the induced stress is the circumferential stress sigma sub c equal to PD over 2T. Okay, PD over 2T. Okay, so this circumferential stress that is obtained when you cut the cylinder this way. Okay, so this one is derived from the equation sigma equal to force over the area. Okay, I will no longer derive, okay, how you come up with this PD over 2T, because I assume that on your deformable body, this has been derived already. Okay, so again, we call this your circumferential stress. Another term for it is a hoop stress or a transverse stress. Okay, P pertains to the pressure, okay, inside the vessel. Di is inside diameter, and T is the thickness of the plate. Okay, this is your induced stress on the cylinder. Okay, now we consider another cutting plane. Say this time, papagano naman po. We have BB prime. So we cut the entire length. Okay, we cut the entire length of your cylinder. Okay, so we come up now with the remaining section. Okay, so this is where you cut it, BB prime. Okay, so this is the remaining section. Okay, so this naman would result to another later. May klase lang. Until what time yun?
Hanggang alas 5.
Hanggang alas 5 pa. Sige, mamaya. Thank you. Okay. So, this is BB prime. So, this is yung remaining section when you cut the cylinder this way. Okay? So, you come up now with another induced stress. So, again, this comes from stress equal to force over the area, which leads to a longitudinal stress equal to PD over 40. Okay? So this is the another induced stress. So again, this is circumferential, and then this one is the longitudinal stress. Okay, so comparing the two, okay, this is PD over 2T, the other one is PD over 4T. Okay, you try to compare the two induced stresses, okay, which is bigger, which is higher in value.
Circumferential.
It's the circumferential, okay? It's the circumferential, okay? So if you notice, the two varies only with this, okay? This is divided by 2t, this one is divided by 4t, okay? So you divide the value by 2, this one is you divide the value by 4. So if you are to consider which would be higher, okay, which would be a bigger value of stress, ito po, okay, the circumferential, okay, this one. This is the bigger stress, okay? Why? You simply divide it by 2, whereas you divide this by 4. So this is smaller than this one, okay? So this is the bigger value of the stress, therefore, we consider this to be your critical stress, okay? So this is your critical stress. So if this is your critical stress, then this must be your basis for your design, okay? So of the two induced stresses, this is more critical, then this should be the basis of your design. So what will you do now? For design, okay, for a good design, you equate now the design stress to the induced stress of the material. So the design stress sigma D is to be equated to your critical stress. So that would be the circumferential, okay? So this would be PD divided by 2T. And what about the design stress? This can be sigma U over factor of safety, or pwede din po ng sigma Y over factor of safety equal to PD over 2T. Okay? So you have here the two equations. Okay? So again, this is if based on the ultimate, yung design natin, and if based on yield, this would be our equation. Okay? So that is how you design, okay, a cylinder, okay, thin-walled cylinder. Okay, again, you just equate it to the critical stress. Okay? Or, pwede rin naman po, gawin natin, you may equate it both. Okay? You can equate the design stress to the circumferential, and another is you equate this also, design stress to the longitudinal. Okay? Therefore, you would have their two answers. And whichever will yield a higher value, then that would be used. That is just the same as this one. Okay? Okay? So the critical stress will give you the value nung dimension natin, which is more critical. Okay? So this is the ultimate and this is the yield. Now, as I have said kanina, the cylinder or the vessel comes from a sheet of metal, okay? So it's a sheet of metal having this dimension, for example, and then you have here the thickness of the plate. Then what you do is simply you connect the two ends using a weld or a rivet, okay? So this is known now as your joint profile, okay? So ito po yung pinagdugtungan natin, okay? And we consider this a joint, okay, as to its efficiency, okay? So there are cases it is not 100% efficient. So most probably, this would be a Waterloo of your pressure vessel, meaning, okay, so this would be the weakest part of it. That if failure would occur, most likely it would occur here at the point where there is the weld or the rivet. Okay, so we consider now what we call joint efficiency. So what do you do if there is a joint efficiency given? Okay, so the joint efficiency, of course, it will always be presented in unit na percent. Say, so we say 80% joint efficiency, meaning 20% would most likely be the failure. Okay? So, doon po sa pinagdugtungan natin. So, you call it the profile joint. Okay? So, you can join it in two ways. It can be welded. Okay? So, the shaded part here, that's the welded joint. Okay? Meaning, you have your electrode. Okay? The electrode, then it should be melted, and then it would fill in this two the materials to be joined. Okay, then you come up with this welded joint. Okay, and then this one naman po, okay, yung bilog-bilog po na yon. Okay, this represents your rivet. Okay, so this one is a rivet. So you have there several rivets in order to join the parts of your plate. Okay, to come up with your vessel. Okay, so for the riveted joint, this is similar to that of a screw. Okay, so very similar with a screw in its appearance. But then you cannot make use of a tool, say the screwdriver, for this to be disengaged. Okay, so this does not contain thread. Okay, so wala po yung thread na pwede nating ikutin. Okay, using the screw driver for it to be disconnected. Okay, so hindi po ganun. Itsura lang niya po is a screw, but it is not, definitely not. Okay, so we call it a rivet. Okay, so these two, that accounts for the efficiency of your joints. Okay, so we have to account this now on our design. Okay, so kung kanina po we say we equate, okay, the design stress to the induced stress of the material. Okay, so the design stress equal to the circumferential stress. Okay, but then if there is a joint efficiency that is given, instead of using the usual design stress, okay, instead of using this one, okay, instead of using this, we will be using now the lowered design stress. So sigma d prime. Okay, this is if JA is given. Okay, if JA is given, instead of sigma d, you use sigma d prime. Okay, again, we call it the lowered design stress. Okay, again, to be equated to your circumferential stress. Okay, so what is the lower design stress? This is simply the usual design stress, just multiply it by the joint efficiency. Okay, so imo-multiply mo lang po, say 80%. Okay, so you use the decimal equivalent here. So sigma d times 0.8. Okay, 0.80. Okay, so that would be the value of your JE. That is only if JE is given. Again, we will be using sigma d prime, and we call it the lowered design stress. Okay, so this sigma d, this can be sigma u over fs, then multiplied by joint efficiency equal to sigma sub c. Okay, this is kapag, okay, design is based on the ultimate. If design is based on yield, this is sigma y over fs multiplied by joint efficiency equal to sigma sub c. Okay, this is when design is based on the yield. Okay, again, what is sigma sub c? This is your circumferential stress. Okay, PD over 2T. Okay, this would be used only, okay, if you have a thin-walled cylindrical vessel. Okay, naintindihan po ba?
Yes po, ma'am.
Okay. Let us have now number 2. Okay, so this is yung number 2 natin. Okay, so this time we have a thin-walled sphere. Okay, so we have a spherical vessel. So for a spherical vessel, okay, say we use this cutting plane AA prime, or we use this cutting plane B B prime. Okay? In any way po natin na siya ay i-cut, okay, you resulted to the same cross section. Okay? Since it is a sphere. Okay? So therefore, we say that the circumferential stress and the longitudinal stress of a sphere would be the same also. Kasi kahit nga po sa natin siya i-cut dito, okay, you would yield the same cross section. Okay? So the circumferential, the longitudinal, simply equal to PD over 4T. Again, P pertains to the pressure inside, okay, diameter, and then this is the thickness of the plate being used. Okay, so if these two are equal, then this is also your critical stress. Okay, and we say sa design, okay, again, we equate the design stress to the critical stress, okay, sigma L or sigma sub C. Okay, so this is your equation. Okay, you equate the design stress to the induced stress of the material. The design stress, it can be sigma Y over Fs or sigma U over factor of safety. Okay, and your longitudinal stress is PD over 40. Ito na po yun. PD over 40. Okay? So, coming from this equation, pwede ka na pong mag-solve dyan ng thickness. Okay? Kung i-substitute po yung mga value, then you can solve now for the thickness. Okay? So, that is the thickness of the plate, okay, being used, okay, in forming your spherical vessel. Okay? So, yun po ang ibig sabihin. Now, the same thing, katulad po nung sa cylinder kanina, if there is a jointed seam, okay? So, ang jointed seam po, yan po ang ginagawa pagkasama po, okay? So, ang gagawin po natin is yung lowered design stress. Kaya ang ginagamit po natin ay sigma D prime equal to your circumferential or longitudinal stress, okay? Because they are the same, okay? This is PD over 4T. Kasi po yun ay longitudinal. Equal to your lowered design stress. So this is the original design stress. Then simply multiply that by the joint efficiency. Okay? So ganun lang po. Pag may joint efficiency, okay? So ang aalalahanin po natin is to use the lowered design stress. Okay? So yun lang po yung gagawin po natin. Again, kailan po yung procedure na yan? Only when we have there a thin-walled, okay? Thin-walled pressure vessel. It's either cylindrical o kaya po ay spherical, okay? So the two varies in their equation, okay? As a cylinder and as a sphere, okay? So dun po natin. May question po ba? Hello?
Wala naman po, ma'am.
So from those equations, okay, masosolve po natin ang value ng thickness. Okay, so we are after the thickness of the plate being used para po dito sa atin na design. Okay? So you simply recall or you simply read po yung problem, okay? So, and then see if it is cylindrical or spherical because they have different equations, okay? Now, what about if we have a thick-walled vessel, okay? What about if we have a thick-walled vessel? Again, for a thick-walled vessel, okay, your T over D sub I, okay, thickness over di, this diameter, okay, should be greater than, okay, this is greater than 0.1, okay, so the value is greater than 0.1 to be called a thick-walled cylinder. Okay? So, ano yung thick-walled cylinder natin? Okay? So, ang ginawa po doon, okay, ang gagawin po, ito po yung atin na cross-section, ito po yung thickness, this will be divided into tiny strips. Okay? So, yung tiny strips po kasi na yan, okay, yan po yung ginagamit po natin for a thin wall. So, ang tinatanong dyan ay ilan yung magagawa mo. Okay? Parang kaya niya bang i-accommodate ilan, okay, noong mga pieces na ito po. Okay? So, yan po yung sa thin wall. So, ilang thin wall ang magagamit natin to come up with a thick walled vessel. Okay? Parang ganun. In terms of the thickness. Okay? So, yun po yung ating idinidesign po. Okay? So, ang pinaka-appropriate pong gamitin, okay, in designing a thick walled pressure vessel is what we call po yung Lame's equation. Okay? So, ang ginagamit po natin dito is the Lame's equation. Okay? So, paano po iginagawa ng Lame's equation? Parang yung iyong pong thin wall, hahati-hatiin niya into several na mga thin wall. Okay? So, yun po yung nangyayari. Okay? Na ano po nila, na-i-invade po nila yung entire thickness. Okay? So, yun po yung ginagawa dito. Okay? So, ito po sa thin wall pressure vessel, okay, yan po yung ating titingnan. Okay? When we will be applying this Lame's equation po, okay, para masagot po natin, okay, yung at malaman yung particular thickness ng material. Okay? So, how do you do that? We have here our Lame's equation. Okay? So, this is the first one. The hoop stress on the inner fiber. Okay? So, it's the hoop stress on the inner fiber. Ito po yan. Okay? So, ang nandito po, yan po yung sigma T sub I. Okay? So, ito po yan. Hoop stress on inner fiber. So, how do you know the value? You use this equation po. Okay? Sigma T sub I is equal to Pi quantity Ri squared plus Ro squared minus 2 poro squared over Ri squared minus Ro squared. Okay? So, ito po yung gagamitin natin equation, okay, for you to solve for hoop stress on the inner fiber. Okay? So, yan po yung gagamitin natin. Yun naman po kasunod. Okay? This is hoop stress on outer fiber. So, ito naman po yung stress doon sa point 3 po natin kanina. Yung nandun sa labas, okay, na fiber. And then the third one, this is your longitudinal stress. Okay? Ano lang po nito, paki-correct. Okay? This is not sigma T sub O, but rather, this is sigma sub N. Okay? Equal to Pi Ri squared over Ro minus Ri squared. Okay? For the hoop stress, 2 Pi Ri squared minus Po Ro squared plus Ri squared. Okay, so this would be the hoop stress on the outer fiber. And then the last one, hoop stress on inner fiber, Pi Ri plus Ro squared minus 2 poro squared over Ri minus Ro squared. Okay, so those are the Lame's equation. Okay, now let us take each one component para po dito. Pi, that would be the inside pressure. Okay? So, kung ano po yung pressure ng fluid or ng gas inside the vessel, parehas lang po ating gagamitin. Okay? Yung po ang Pi. Sunod po, Ri plus Ro squared. Okay? So, yung Ri po, this will come from the diameter na binigay po. So, inside diameter, you simply have it, okay, divided by 2. But what about Ro? Okay? Yung Ro po, sigurado po, hindi po yan ibibigay. Okay? So, why? Kasi po, kung bibigay po yung Ro, we can easily obtain the thickness, okay? That is simply equal to Ri plus thickness, okay? To obtain the outside radius. Kaya, hindi po talaga ibibigay yung isa doon sa dalawa. Ro o kaya Ri. Okay? But then, the other one naman po, Okay? You have there po yung piece O. Okay? Ano naman yung PO? Okay? This is the outside pressure. Okay? Kung wala pong ibang gas doon sa paligid, okay? Ang gagamitin na po natin, okay? Ay yun po standard atmospheric pressure. Okay? So for PO, we will be using the standard atmospheric. And that is equal to what? Hello? Ano po ang equal na to?
180 yan po.
Okay. So, for the PO, okay, ano po ang ating gagamitin na pressure sa labas, okay? So, we assume, katulad po ng sinabi ko kanina, it would be yung air po, okay? So, we will use here 101.325 kilopascal or 14.7 14.7 PSI and 1 atmosphere. Okay? So, yan po yung mga gagamitin po nating value ng P sa boat. We call this the standard atmospheric pressure. Okay? RO, RI, so yan naman po ay nandun na sa table po natin. Okay? Okay, so ano nga po sinabi ko dito? We are after the thickness of your plate po na gagamitin. Okay? So definitely, again, maalin lang po doon sa inside at outside dimension, yun po yung ibibigay. Pero not totally po yung dalawa. Okay? So that is how you compute po for the hoop stress on the inner fiber. Okay, the second one, this is the hoop stress on outer fiber. Okay, so ito naman po doon sa labas, okay, ng cylinder po natin. So sigma T sub O equal to 2 pi Ri squared minus PO, quantity RO squared plus Ri squared all over RO minus RI. Okay? So, same din po yung mga kinuha parameter dito doon sa sigma T sub I. And then the last one po, you have there the longitudinal stress. Okay? So, the longitudinal stress is PI RI squared over RO minus RI and then multiplied by T. Okay? So, you call this your longitudinal stress. Okay, so you have here now yung tatlo po na nakita natin, okay? That talks all about stresses, okay, in the cylinder or in the sphere. Now, you compute for the thickness of the plate, okay? So, yun naman po lagi ang hanap natin, what thickness is to be used, okay? So, we have here po two equations, okay? Two equations for the thickness. The first one is when material is ductile, and your equation 2 is when your material is ductile. Okay, one is for brittle, two is for ductile. So if you know that the material is ductile, okay, you find value of the thickness using this equation. Okay, kung brittle naman po, ito naman po yung equation po natin na gagamitin. Okay? So, you look at the equation now to obtain the thickness, right? Thickness equal to di over quantity sigma y over sigma u minus 2pi raised to 1/2 minus 1. Okay? So, ari lang po. Okay, so kailangan lang po natin is to solve first for sigma T sub I. Okay, so yun muna po, necessary pala po, bago natin ma-solve yung thickness dito, dapat ma-solve muna natin yung sigma Ti. Okay, so we go back to sigma Ti. So ito po yan. Okay, so we need to have po yung sigma t sub I before we can compute for doon po sa kanyang thickness. Okay? And then take a look at sigma t sub I. It's a function of RO. Okay? So, ang gagawin po natin si RO, since siya po ay unknown, okay, pwede mo po siya gawing Ri plus T. Okay? Para po magkaroon ng numerical value or exact value. Okay, nakuha po ba? So, ari po RO dito, ang gagawin mo po dyan, ipapalit mo po ito, Ri plus T. Ri is unknown, but then T is unknown. So, pwede po yun gamitin natin doon, okay? Para we come up with sigma T sub I na siyang isa-substitute naman po natin, okay? Yung sigma T sub I na yun.
Pwede nila nilalagay sa ano lang
Okay, so any question po? Hello? Okay, so ang gagawin po dito ha, it should be expressed in Ri plus T. Ri is given, okay, and then this is the unknown. Okay, tapos siya po yung isa-substitute natin to say equation 2 or equation 1. Yung pong sigma T sub I, yun po yung ipapalit po natin. Okay, so again, as I have said, okay, the procedure po that we will be applying will depend upon the type of material, okay? Whether it is ductile or brittle, okay? And also the, in this case, it is the limiting criteria, okay? So, may question po o malinaw na?
Malinaw naman po.
Okay. So, let us, yes, Jared.
Ma'am, doon po sa limiting criteria, di ba po thickness po yung thickness over diameter? Paano, di ka po ang hahanapin po ay thickness? Ano po?
Okay. Okay, correct. Okay, so tama yung sinasabi ni Jared. Okay? So, ito po, okay, sabi ko nga sa inyo, bago tayo magsimula on our design, okay, before we could start our design, necessary that we know first whether it's thin-walled and thick-walled, okay? And to do that, you start with your limiting criteria. But then, take a look at the limiting criteria. It is a function of the unknown, okay? T is the unknown. So, how can you solve for the limiting criteria if this is the unknown, okay? So, tama po yung sinabi niya. This is just the same as that of the compression, okay? So, if this is the case, this is unknown, you cannot proceed with the limiting criteria. So, your first move is to have an assumption, okay? So, you will have your assumption first. So, what do we assume? Parang yung sa compression, we assume first, case 2. Okay, dito, we assume to use, we assume thin wall. Okay, so that would be our assumption. This is our first assumption, assume thin wall. Then you use the procedure, okay, in designing a thin wall. Okay, that is simply equating the design stress to the circumferential or to the longitudinal stress. Okay. This is the critical stress, okay? So, and then you'll have your answer, okay? So, if you have your answer already, yung thickness na na-obtain mo po, okay, you are not sure if this is correct or not, okay? So, you need to test this value, okay, to see if your assumption is correct, okay? So, you need to test this. So, how would you test? You go back to the limiting criteria. Okay, that would be T over D sub I. So this T should be equal to this. Okay, so this is to be substituted to D over D sub I. Okay, and if this value T over D sub I is less than or equal to 0.1, then you conclude it is really thin mold. Okay? And then you say, therefore, use that value of the thickness. Okay? Oh, but then the other way around, if you solve for the limiting criteria, T over D sub I. Again, this T, that would be the same as this answer. Okay? The same as this one. T over D sub I, but then it happened, it is greater than 0.1. Then conclusion, it is thick walled. Okay? And once it is thick walled, we cannot say therefore use this thickness. Meaning, if it's thick walled, then this is not correct. Okay? The thickness that you obtained, assuming it is thin walled, is not correct. Okay? So, therefore, you need to recompute. Okay? You need to recompute using
So, kapag pinatas na natin
the Lane's equation. Okay, so you need to recompute using this. And once you have your new answer, okay, using the Lane's equation, this is final. Okay, no need to again test that using the limiting criteria. No need. The answer you obtain from the Lane's equation, that would be your final answer. Okay? Nakuha na po? Hello?
Yes po,
Naintindihan po ba? Okay, very good.
Opo, ma'am.
Okay? So, let us have the sample problem 1.
Sample ng wastewater.
Dito muna po tayo, sample problem 2. We start with this one, then we'll go back later to problem 1. Determine the safe wall thickness of a 30 inches steel tank with internal pressure of 7.82 megapascal. Yield stress of the material is at 275.48 megapascal. The factor of safety to use is 2. Okay? So you look at this problem 2. Okay? Notice that the given are mostly in the SI. Okay? But in this one, this is still in English unit. Okay? So this is in SI. So if the problem, okay, the given on a problem is in SI, then we are to solve this using the SI unit. Okay? Naintindihan po ba? So, if this is in megapascal, forces are in Newton, okay? Dimensions in millimeter, then we should be solving this on the SI system. Okay? But then, if given are in the English unit, okay, so everything should be in the English unit. But once given is in SI, do not convert this, okay, into an English unit. Okay? It is simply your sigma U and also your sigma Y, which we take values from the design table. These are to be converted from KSI to megapascal. Okay? So you need to convert these two values, sigma U and sigma Y, to megapascal. Okay? If these values are taken from your design table. Okay? So it is on the material specification, okay, that you convert their values into the megapascal or SI. Okay? So what do we use in the conversion? Okay? Just the same as that of the pressure. Okay? For the pressure, 14.7 psi is equal to 101.325 kilopascal. So same conversion would be used here. Okay? So yan po yung gagamitin natin in order to convert. Okay? But then, ano po yung maliwanag? Okay? If given are in SI, then we will be solving that on SI. Okay? I will not give credits or I will not give points on those that would convert this into an English unit and solve it in the English unit. Okay? So if it's given is SI, then have it in SI, your solution. Okay? So yun po yung gagawin po natin. Okay? So let us have this one. We start with the given values. You have there 30 inches. Okay? So that's diameter equal to 30 inches. So this one, let us convert this into millimeter. Okay? So we are solving this on the SI. So convert this in millimeter. Internal pressure, okay, that is equal to 7.82 megapascal. Okay, so these are our given. Okay, what else? So after this is the material specification. So there is no code, AISI number, okay, or code given on this particular problem as to the type of material. So for the material specification, it is simply specified this is a steel tank, okay? So a steel tank with sigma U, okay, our sigma Y is given 275.48 megapascal, okay? Again, this is given. Okay, so this is the property of the steel tank. Okay, after the material specification, we have their factor of safety. Okay, so Fs is simply equal to 2, and this is just a given. Okay, so this is the factor of safety. And then let us have the design stress. Sigma D is equal to sigma Y over factor of safety. Now, the question is, how do you know that you will be using sigma Y over factor of safety? Okay? You do not know whether the material is ductile or brittle. Okay? Since it is the only given here, okay, so we have to base the design on the yield strength of the material. Okay, that is why we make use of sigma D equal to sigma Y over the factor of safety. Okay, so just have here now the value. This is the value of your sigma Y, and this is the factor of safety, so you can compute for your design stress. Okay, and then after the design stress is the time for you to decide, okay, which procedure would be applied. Okay, so you need to know whether the given vessel is a thin gold or a thick gold. Okay, so you will be using the limiting criteria in that case. Okay, so you solve for the limiting criteria, T over D sub I. But then as I have, ano po natin, T is the unknown. Okay, so wala pa po tayong makukuha pong value. Okay, so what do you do next? Okay, after knowing that T over D sub I, we cannot find its value. Okay, since the unknown is the thickness. So you simply assume. Okay, you assume first it is thin wall. Okay, and once you assume it is thin wall, you can now make use of the procedure for thin wall. Okay, so ano po yung ating procedure for thin wall? We simply equate, okay, the design stress to the induced stress of the material. Okay, so the design stress is sigma D, and the induced stress is your circumferential stress, and this is equal to what? PD over 2T. Okay, so you have here the value of P, you have the value of the diameter, okay, and your sigma D can be solved from this. Okay, so therefore you can solve for thickness coming from this equation, coming from this assumption. Okay, now we are not sure if this is correct. Okay, so we'll go back to the limiting criteria. Okay, so you make use of this T over D sub I. Okay, so you make use of this thickness dito po. Okay, and then see what is the value. Okay, if this value is less than or equal to 0.1, then this answer is correct. But then if not, greater than 0.1, you need to recompute. Okay? Nakuha po? Hello?
Yes po, ma'am.
Okay. So try to solve first this problem 2 on your own. Okay? try to solve it first, and then afterwards, okay, we'll have our problem 1. Okay, so try to solve it first. Nasasagutan po ba? Hello?
Opo, ma'am.
Okay, so let us have the answer here. Okay, you may chat your answer po on our chat box here. Okay, so we have here first. What is DI? This is 30 inches converted to millimeter. What is the value?
762 mm.
Again?
762.
Wala ko indication.
Good lang. Again, what is the value? Hello?
762 mm po.
7? No, I am
762
referring to the inside diameter. 762 mm. Okay, so this is 762 mm, and then this one would be 275.48 megapascal. Then you divide it by 2. So give value would be 100. This one.
37.74 po.
Ulit.
137.74 po.
137.74. Huh? This one.
May revision package sila pa.
137.74 or 0.4. Hello?
0.74 po, ma'am.
Tama po ito, Alex.
Hindi pa na revision
Yes
consultation
po.
package pa lang.
Okay, so this is in megapascal. Okay, 137.74 megapascal. Now, you go to the limiting criteria to know what procedure would be applied. Okay, so you assume thin bolt. Okay, and then we equate the design stress to the critical stress, PD over 2T. Okay, so having that, okay, yung T would be equal to what? It would simply be yung pressure, okay, 7.82 megapascal times your DI, that is 762 mm, divided by your design stress, okay, which is 137.74 megapascal, and then multiplied by 2, okay, PD over 2T, okay. So we come up now with thickness equal to what? 21.631. Tama po ba yon? Kindly check the others.
Yes po, ma'am.
Same answer.
21 point, ano nga sinabi ko, anak?
631 po.
631.
631 mm. Okay, so this is the thickness. But then, this answer of ours, okay, this comes from our assumption. Okay, we simply assume that this vessel is a thin wall. So we need to verify using the limiting criteria. So you use this answer of yours, 21.631, you make use of the real value, then divided by 762 mm. Okay, so both in mm, so you can cancel them po, okay, giving us T over D sub I equal to what?
0.0283 po.
0.028, okay, 0.028. Now, you look at the value, okay, so since your T wait lang. So since the value of T over D sub I, okay, you are sure this is less than 0.1. 0.028 is less than 0.1. I do not want to see that you state here T over D sub I less than or equal to 0.1. No. You see the value here, 0.028, and that is definitely less than 0.1. So I do not want to see here or equal to 0.1. Okay? So hindi po. Less than 0.1. So since the value is less than 0.1, it is really thin walled. Okay? Therefore, it is thin walled. Therefore, you use this thickness. Okay? 22 mm. Okay? So this 22 mm, that would be the standard size for this. Say 22 mm. So what is again the standard size? If it is on the SI, it should be the next whole number. That is why we use here 22 mm. Okay? No fractional part for the dimensions in millimeter. Okay? Even if you obtain there, the thickness is 21.358. Okay? Even though it's less than, or if you are to round this off, okay, it would be most likely 21, okay, but then you will be using the next higher number, okay, so that's the same 22 mm for this case, okay. Naintindihan po ba? Okay, so this is our final answer. We use the thickness equal to 22 mm. Question? None?
Wala
No.
pong.
Okay, I hope you yield the same answer po. Okay, so everybody. Okay, let us take the case of sample problem 1. Determine the bursting steam pressure of a steel shell with diameter of 10 inches and made of 1/4 thick steel plate. Okay, joint efficiency is at 70% and the tensile strength is 60 KSI. Okay, so you look at the given values. So this one would be the diameter. Okay, this one would be the thickness. Joint efficiency 70, this is your JE, and then this 60 KSI, this is your sigma U. Okay, you're asked to find the bursting steam pressure. Okay, so let us list down the given values. So we have the diameter equal to 10 inches. we have the thickness equal to 0.25 inch or yan po yung 1/4. Okay? 1/4 inch po. Yan. And then you have their JE is equal to 70%. So these are the given values. Now we have the material specs. Same thing, it states simply steel, okay? And then from the word steel shell, okay, this would mean this is spherical in form, okay? So this is spherical. So ang gagamitin po natin are all equations for a spherical vessel, okay? So steel having sigma U or the tensile strength equivalent to your ultimate strength equal to 60 KSI. Okay? Now, let us have now the factor of safety. What would be the value of the factor of safety? Okay? You'd go again doon sa problem, okay? And see the problem, okay? So, determine the bursting steam pressure, okay? So, you are asked to find the bursting steam pressure, okay? The pressure to which your vessel will explode or will burst, okay? So, in order for this to burst, okay, you don't need a factor of safety. Because if you apply here a factor of safety in your computation, okay, then the pressure that we will obtain will be a safe value of the pressure. Okay? That is why in this case, in this particular problem only, okay, we will not incorporate a factor of safety. Okay? So we simply leave it blank. Okay? Kasi we are looking for this bursting steam pressure. Okay? So naintindihan po ba? Naintindihan po? Ibig sabihin ko, hello?
Yes po, ma'am.
Yes po.
Okay.
Yes po.
So, we leave the factor of safety wala pong value. Okay? So, we go now to the design stress. Sigma D is equal to sigma U divided by factor of safety. How do I know that it would be based on the ultimate? Since on the material specification, it is only one given. Okay, kaya we will make use of it on our design stress. Okay, now factor of safety, again we ignore the factor of safety because we are looking for the bursting steam pressure. Okay, so therefore your sigma D is equal to your sigma U only. Okay? It would be equal to your sigma U only. Now, so you are given here joint efficiency. Okay? So since JE is given, we will not be using only the design stress, but rather, okay, we are to use the lower design stress, sigma D prime. Okay, so we will be using the lower design stress. Why? It is because you are given a joint efficiency. Okay, so sigma D prime is equal to your sigma U, and then you have to multiply this by your factor of safety. Okay, you have to multiply this by your joint efficiency. Okay, so sigma D prime, okay, is your sigma D multiplied by your JE. Okay, this is your joint this is your lower design stress. Okay, so sigma D multiplied by JE equal to your sigma U. Okay. Now, so given this now, okay, so therefore your value of your sigma D, okay, would be equal to your sigma U divided by your JE. Okay, and then ano po yung kasunod natin na gagawin? Okay, determine whether it is a thin walled or a thick walled. So you use the limiting criteria. Okay, so you have their T over D sub I. Okay, so you have their the value of the thickness 1/4. Okay, and then you have there your DI is 10 inches. So you can find the value of this T over D sub I. And then from there, you would know now what particular equation is to be used. Okay, so if this happens to be, okay, less than or equal to 0.1, proceed to the procedure of a thin wall. Okay, and if this is higher than 0.1, then you use the Ames equation. Okay, kindly continue. Okay, kindly continue to determine the bursting steam pressure. Okay, so paki-ano muna po natin. Try to find the answer po. Okay. So you solve it on your own po muna, then we'll continue later pa. Okay, so what is the value for the limiting criteria? So thickness is 0.25 of an inch divided by inside diameter is 10 inches. So you cancel this out, and this is equal to 0.025. Is it correct? Hello?
Opo, ma'am.
Yes po, ma'am.
Okay, so since the value, okay, so since your T over D sub I, this is a less than 0.1, then it is a thin wall. Okay, so since thin wall, okay, you use now the procedure, okay, in designing a thin wall vessel. Okay, so we say for a good design, okay, you are to equate the design stress to our critical stress. Okay, so what is the critical stress here? That would be PD over 40. Why am I using this one? It is because this is a sphere. Okay, so it's a spherical vessel. Okay, PD over 40 po yung gagamitin natin. And what is this design stress? We will be using the lower design stress. Okay, so we use the lower design stress. So the lower design stress, that is being multiplied by your JE. Okay? So what is then now the value? What is the value for the pressure po that we obtain coming from this equation? What is your answer?
$4.2 KSI po, ma'am.
Paano nga po ako sa chat box po? Okay, correct. So pressure is simply equal to 4.2 KSI. Okay, so we call this your bursting, okay, steam pressure. Okay, so meaning if we will be using this pressure, okay, on the vessel, okay, so most likely it will explode. Okay, but if we incorporate here factor of safety, Okay, just like the usual that we are doing, if we include here a factor of safety, what we will have pressure here will be a safe pressure. So no bursting would occur. Okay, that is why we eliminate the part of the factor of safety on our design for us to be able to obtain this fact. Okay, so do you have any question? Nan? Hello?
Wala naman po, ma'am.
Wala
Wala
naman po.
naman po.
Okay, so I think that ends our session for today, okay, on the design of pressure vessel. Okay, again, if this will entail po, okay, greater than 0.1, you will be using the Lame's equation, okay? I'll end the presentation now. You open your camera for a quick attendance check. Is Rio is around? Wala. Alex?
Ako na lang po, ma'am.
Okay,
Game po.
okay.
1, 2, 3. Isa pa po. 1, 2, 3.
What about UV? Is UV around? Wala din.
Just for this.
Sivat? Okay.
Yes.
Okay, I'll end the
Okay
meet
na
now.
po, ma'am.
Bye. I'll see you tomorrow. Okay, bye.
Thank you po, ma'am.
Thank you po, ma'am.
Thank you po, ma'am.